Matter, in terms of size, exhibits a hierarchical structure. At the largest scale are molecules, which are made up of atoms. The atom, the fundamental unit of chemical elements, comprises a nucleus surrounded by electrons. Within the nucleus, which is significantly smaller than the atom itself, are protons and neutrons. These particles are roughly equal in size but distinct in charge. They, in turn, are composed of quarks, which are among the smallest known particles and are held together by the strong nuclear force. Beyond quarks, the subatomic realm includes other fundamental particles such as leptons and bosons, each contributing to the intricate tapestry of matter and the fundamental forces that govern the universe. This is our current understanding of the composition of matter. The special theory of relativity suggests that a tiny amount of mass can be converted into a large amount of energy, and vice versa, based on the principle of mass-energy equivalence. It is known today that the mass defect associated with a nuclear reaction, or any other events in the universe that create a mass defect, results in a large amount of energy. The energy associated with a mass defect appears in two ways. One is the kinetic energy of the reaction products, for example, alpha particles, beta particles, neutrinos, etc. The kinetic energy of particles demonstrates that they are expelled by some physical actions. The second is as high-energy photons, namely gamma rays. Charged particles emit photons when they are excited or agitated. Since particles have mass, to get excited or agitated, they need something to physically influence them. So fundamentally, if a particle emits radiation, that means some external force influenced that particle. One can conclude that both the emission of particles and the emission of photons associated with a mass defect is the result of physical activities associated with the mass defect. This leads us to assume that perhaps the missing mass explodes. The speed of the reaction product shows that the explosion is significantly greater than any type of chemical reactions. In fact, neutrinos travel at a speed close to the speed of light. As nearly massless particles, we can assume that the speed of the neutrinos may be the explosive velocity of the mass defect. So, the release of energy with a mass defect that occurs in a nuclear or any other types of reactions or event is the result of the explosion of the missing mass. When a mass defect explodes, it propels the reaction products at very high speed, and when they collide with surrounding particles of matter, it results in the generation of heat energy. This contradicts the mass-energy equivalence principle suggested in the special theory of relativity by Einstein. Mass defect is a universally occurring phenomenon. Every active star in the universe, supernovae, neutron-star collisions, black hole mergers, etc., are sources of large-scale mass defects. This leads to the interesting possibility that space in the entire universe is filled with this type of matter, and the hierarchy of the matter, in terms of size, goes well beyond the standard model of particle physics. This explosion transforms the matter in the nuclear density to a matter that fills the space. We can calculate the energy associated with a mass defect by finding the density of the matter in space and the quantity of the missing mass. So, the mass-energy equivalence equation will be replaced by a formula that describes the energy density in matter when it explodes. I am Joseph George, and I am preparing my paper for peer review. Thank you for watching.